Another concern is, well, how do I go and combine these methods with existing NLP and the prior knowledge we have? Well, there are simple ways to do that. We've mentioned that you can just add your features to the model. You can also add the features learned by the model as extra features to your model. And that has been done, for example, by Trojan and collaborators. Then something a bit more involved, the kind of thing that Richard has been talking, is integrating the ideas of representation learning and deep learning with known ways of doing things in NLP, like parsing. We talked about recursive and recurrent networks for trees and chains to do that. And I think there's a lot of open and interesting questions on how to use our prior knowledge of language processing and combine them with the idea that we want to learn representations, we want to learn multiple levels of abstraction. So there's your research that's here. Another concern that has been expressed is, oh, this is slower to train than linear models. Well, that's true, but by a small constant factor. So that's not a big worry. More importantly, if you compare to non-parametric models, which is what you should compare them with, because these are really non-linear models, those deep learning methods are much more compact, use much less memory than non-parametric models. And they can be very fast during inference and test time, just because it involves a few matrix multiplications. Some people have worried that, okay, well, these more complicated models, they must need more training data. It's true, but they can take advantage of large quantities of unlabeled data. And in fact, one of the things we've shown is that if you have lots and lots of unlabeled data and very few labeled data, they really shine. The interesting thing is we can also take advantage of a really large data set. Recently, Google has trained huge neural nets with 1 billion connections for object recognition. But I know they're also working on language models that they're applying to advertising in particular. That are pretty large models. Here's another concern that's kind of connected to something we discussed a bit earlier about encoding prior knowledge and the structure of language. So it's true that there's not sort of an obvious way, but there's a lot of freedom at the same time. So you can choose architectures, and we've talked about a few choices that make sense for your problem, for your domain, make sense based on the linguistic prior knowledge that you have. You can include human design features in the first layer, just like you do for a linear model. And keep in mind that the goal of the whole thing is to learn the representation. So let's take advantage of that. Another concern that has been expressed is model interpretability. We get these continuous representations. How do we make sense of that? We use symbolic features like noun phrase, verb phrase. So that's true, but then semantics and meaning and a lot of things in language is fuzzy, and words have soft relationships to each other. So maybe these continuous representations are meaningful and make sense for NLP. And if you compare it to other approaches like huge feature vectors that combine and conjunctions of different features, they're not always easy to interpret either. That's a more sort of interesting and theoretical concern. When you train these things, you're facing a non-convex optimization problem, and as we've seen, you have to think about the local minimum issue to some extent. So maybe we're going to get bad results because of this. Well, actually, you can pretty much always show that you can't really do much worse than a convex learner. For example, what you can do is you can initialize your non-convex optimization with the solution of a convex optimization, and then go with further optimization in which you're guaranteed to improve. This has been done for SVMs, so you can take an SVM which is convex, and has a fixed feature space. And then you can either make the cost function non-convex or make the feature space adaptive, and now it becomes a non-convex optimization. You can think of the representations we are learning as really learning a feature space for SVMs. And if you think about it this way, then this non-convex step is guaranteed to improve. So even though the optimization problem is difficult, since you can in principle at least initialize from the convex optimization problem, like logistic regression, for example, in practice you never do worse than the convex sort of variance that we are used to. And I've said a lot of negatives, but there are advantages. It's quite interesting to see that in spite of the small number of researchers that have been in this intersection of deep learning and NLP, there are already many state-of-the-art results on a large number of tasks that I've been talking about. Another interesting point is that you can get really fast implementations because it's all matrix computations, and that these are well suited for CPUs and GPUs and parallelization. But I think the real advantage is statistical. The real advantage of deep learning is that you're able to learn these high-level abstractions from data, and that's a huge payoff. And the reason it's a huge payoff is that the world around us, I believe, is organized with a hierarchy of abstractions. And what these methods are really trying to do is discover the underlying factors of variation and disentangle them. And as we improve them, well, first of all, we discovered that they do that naturally, but I think we can do even better. And when you're able to do that, you're able to solve your problems much easier, much more easily. As soon as you go through more abstract representations, things like transfer to other domains or other languages become much easier. And I think that's when the real payoff of deep learning is really there. So we're done and have time for questions. Yes?
I have one question about the choice of choosing the food function, the function or the food function.
Yes, yes.
So there's one problem, for example, by not those embedding from the website, for example, from the food work. And
Yes.
why I want you to choose the other function other than the hard function.
Yes.
It could be exactly the right or
I don't think the hard branch function is crucial in the covariate work.
but if I use the further model and follow the neural language processing and follow that, then you can see
No, you can use, in principle, you can use other linearities higher up. It doesn't have to be the same. So the question was whether we should use the same linearities at other levels and covariates of our branch, or you don't have to. Yes?
I have a very simple question about interpretability. So let's say you make a sentiment classifier with a deep belief network or something,
Yeah.
and it makes a mistake.
Yeah.
How can you tell why it made that mistake?
Okay, that's a good question. You guys have ideas? Well, so one thing you can do in general for any deep learner is you can trace out which parts of it were involved for a particular example. So especially if you have sparse representations, there's going to be only a few units that are active for that example. And we've shown a little bit of that. You can visualize what each of the units in the network is doing. For example, you can visualize that by showing which input it likes the most. That's sort of first degree of visualization.
So I guess the answer depends also whether you have a bag-of-words representation or a sentence. For these kinds of recursive models, you can look at every single node of the tree and see what it thinks. And then, as you combine another word, you can see how that changes the sentiment and whether it does that correctly or not. So there, you can interpret it and you can just see right away, like, this word is a problem. And then the question is more like, well, knowing that it's wrong is one thing, but being able to fix it is another thing. So one of the things, for instance, that's why I showed this flawed example, and basically what that led me to do was looking back at my original training data, doing a simple graphing and showing, oh, when does flawed appear? Why would flawed be so indicative of a positive mood review? And then you kind of see something about your data, and if there are certain phenomena that aren't in your data, then the model won't be able to pick that up. And it's those times where your data set is too small that you might have to add your own knowledge to prevent things like that from happening. And for bag of words models, it's very clear. You can just sort of see the weight in your matrix. You can see a weight for that specific word being very high. And then you can actually also take out certain words in the bag of words representation and see if that changes your problem. So there are lots of different ways you could do like error analysis.
Hi. So for one of the applications you mentioned, modeling relations with matrices, and you might have covered this already, but how do you deal with relations that are not symmetric, like causality and temporality?
Which one? In sentences or for databases?
I
think neither of the applications we talked about assume symmetry of the relations, because different parameters were used for the left-hand side and the right-hand side. So, it doesn't have to be symmetric at all.
Thank you. Yes.
So two of the important features of deep networks, that is the unsupervised learning of the features and the discriminative learning of the features, have their counterpart in the kernel world. Like kernel PCA would be the equivalent of the unsupervised learning of the features, and kernel learning, all the different methods for learning the kernels, would be the equivalent of the discriminative learning of the features there. Could you position what is your feeling about advantages and disadvantages of?
With respect to kernel methods?
Yes. Yeah.
I've written whole papers about that.
Yeah.
So I think Chris at the beginning briefly explained something about the theoretical motivations behind these representation or deep learning methods compared to non-parametric methods, which include kernel machines. And essentially, it's about the expressive power that even though a kernel machine can represent any function, it may need a huge number of components to do that. And you can understand that geometrically in terms of how they generalize. And they generalize essentially locally. In other words, what you learn from an example allows you to generalize in the neighborhood of similar input configurations. With these methods, there is at least the potential, if the data has the corresponding implicit priors, there's the potential to generalize non-locally and to express the same kinds of functions using much more compact models. And so from a statistical point of view, you expect, if those priors make sense for the world around us, to generalize much better. So these are sort of theoretical arguments that I've been making in a few papers. But there are also practical concerns like training time scales essentially linearly with these methods, whereas with kernel methods it's more like quadratically. And of course there's a memory issue that also is pretty bad for kernel methods. But for me the most important is sort of from a fundamental statistical point of view, we can if the underlying distribution satisfies these priors, and these priors are basically the unsupervised prior, and the fact that the world can be compactly expressed as we do represent the world ourselves, as sort of composition and abstraction on top of abstraction. This kind of prior is not exploited in kernel methods, and so they're kind of doomed in a statistical sense.
I also a quick answer to that. One is, for kernel methods, the input, you still have to think about sort of what kind of input representations you give to your documents, and that, you know, that those kinds of methods, the deep learning methods, actually learn that representation. The other one is,
so here's another interesting connection. When you have a kernel method, you have essentially a feature space, which is implicit, and then you use a kernel trip to do efficient completion in that space. And then you have a loss function. So you can have all of the same things. The only different aspect here is that the feature space is learned. In kernel methods, someone hands you the feature space, and usually you choose a feature space that's pretty simple, like the one arising from the Gaussian kernel, or linear, which is no feature space at all, I mean the original input space. So the big difference here is saying, okay, because kernel methods are great, but really we need to learn the feature space. How do we do that? That's what we're trying to do.
Back. So one is that you can actually combine this unsupervised and this semi-supervised. Like you can run kernel piece A, but then you have some other classification problems. It's not clear how to, you know, use the representation you learn in one with the other. And the second one is you can incorporate sort of the structure of the problem. So if you know you have like a linear chain kind of problem, then you can use a recurrent neural network. If you have like a hierarchical structure or a tree structure, you can use recursive neural networks and so on. And I feel like incorporating sort of those kinds of structures deep learning methods are, I think,
when the deep learning is applied to some application at say, let's say word sense some equation, and if it does not produce good results, suppose how to conclude that the data itself is not differentiable or not able to be learned, or the parameters are the main concern which are not properly tuned.
The usual things we do in machine learning, right? So we compare the results we get with simpler models. So you start with linear models or with known baselines like a kernel method, and you compare the results both numerically and in details to see what's going wrong. If you're doing worse than the linear model, then obviously something's wrong with your optimization. So there's no magical recipe, but when you do machine learning, you need to understand, and it doesn't do what you want, you somehow need to understand a bit what the method is doing and the domain in order to make sense of what's going on. It's like a policeman looking for clues, and it's not easy.
But does it mean that necessarily nonlinear models must outperform the linear models, or?
Yes, they should outperform the linear models. If they don't, then you're doing something wrong. For sure, they should outperform the linear models on the training data. And on the test data, of course, it depends on whether there are nonlinearities present to be captured in the first place, but for most problems, there are. So that's why a sort of obligatory baseline is the equivalent linear model.
Thank you.
So if you recursive encoder, just you agree that do you know any more principal ways to learn from that structure?
So is there a more principled?
For example, design and write variables, which is the best structure for this one?
So is there a more principled way to learn a tree structure for a sentence given a certain problem? Well, I think there are two cases. I think the standard case is you just use the big right parse. So you take, either a Stanford parser, Berkeley parser, another like state-of-the-art parser, and you fix that representation, and then on top of the syntactic structure, you learn the semantic structure. That's actually what we did do in the paraphrase detection and relation classification problem. For sentiment, it turns out it actually works slightly better to let the model decide what tree structure it wants. And in those cases, you won't get the kinds of tree structures that you're familiar with from parsing, because the model will care more about sentiment words and merge those first. And I think the similar ideas would be applicable to data models, but I couldn't think of another, I'm sure there are other principled ways of coming up with tree structures.
So what Richard has been talking about is connected to sort of a principled equivalent probabilistic model. It is just a kind of approximation of the long likelihood where instead of summing over all the three configurations, we are taking a max, and in fact it's an approximate max because we are using a greedy approximation. But we understand these approximations, and people who do structured output models, for example, and machine learning do similar approximations and understand them.
Do we have time for one more question? Yeah.
Regarding the size of your hidden layers, are there cases in which you would like to prefer smaller hidden layers or larger hidden layers with sparse coding?
Yeah, so the question is, would you prefer smaller hidden layers or larger hidden layers with a sparsity constraint? And so just to give you an intuition again, the sparsity constraint essentially creates a bottleneck. And I assume you asked about autoencoders, for instance. So for autoencoders, they really only work if they have this informational bottleneck. And in some vision cases, sparsity actually works better, and then you can also increase the layer size more and more. And in some vision cases, that's really ideal. For recursive autoencoders, there's no point in creating larger space because you want to, in the end,